So let me define a randomized algorithm more formally. We will only talk about case when the output is 0, 1. This is not hard to assume. You are a computer scientist. You like Boolean values. Let's say that our goal is to output succeed or fail, 0 or 1. And now a randomized algorithm uses some randomness. This is the main difference from a usual algorithm. In a usual algorithm, all steps are fixed. You do this depending on the input, you do the next step, and so on. But in this case, at some point of the algorithm, you just toss a coin, some randomness, and depending on the random value, depending on the output, you choose what to do. This was clear in the context of the previous algorithm where our randomness was in choosing or picking Z. Depending on the Z, we calculated X transpose Z. So similarly, there can be a general algorithm to calculate some value where we want to output 0, 1. It might be a random string to use to decide which way to go, and then we answer. The important point is the output does not depend just on X. Okay, so this is something which is very counterintuitive from whatever algorithms we have seen. Generally, the output only depends on X. Here, it will depend upon X and some random bit R, which will be chosen randomly through the execution. So, in some execution, might give the correct value because the correct arrow, one of the correct arrow was chosen. Some execution of the algorithm might give incorrect. And not surprisingly, what we need is that probability that our algorithm succeeds is more than some high value. Let's start with 3. So such an algorithm is called a randomized algorithm. Main difference, instead of at every point knowing what we do, at some points we might want to use randomness to decide what to do. That means for some random strings we will get the correct answer, for some random strings we will get the incorrect answer. What we need is that for most of the random strings we get the correct answer. And more importantly, this is a case of confusion for many people, this should happen for all X. That means whatever be the input, for most of the random strings, my algorithm should succeed. So I should correctly write it as probability over the randomness which I am using. AX is correct. This is more than 3/4 for all inputs. This algorithm actually depends on two things. What is the input and what is the random string. And if you have any confusion, look at our algorithm for giant. You will see that X, Y were the inputs and R was the Z which was chosen randomly. Take some time and make sure that you understand this. And now we are allowed to use randomness, and the criteria also is relaxed. We don't need to succeed all the time. We should succeed with high probability. Generally, in the case of randomized algorithms, you can divide it into two kind of algorithms: one-sided error and two-sided error. One-sided error is what you saw in the case of Jay and Viru also. So in this case, if the output should be 1, then we always get 1. Right? So if X was equal to Y, we always got X equal to Y in the randomized protocol. So this is a one side. If output should be 0, if the ideal output is 0, we get 0 with high probability. So this is one side. On one side, we always succeed. On the other side, we succeed with high probability. And the example you saw was of the one-sided error. In general, your algorithm will have two-sided error where on both sides the probability that my algorithm answers correctly is more than some constant. In the case of one-sided error, we saw that if my failure probability was half, I could increase it to 1 by 1024 by repetition. Now, what about two-sided? So again, I have an algorithm which on the randomness succeeds with high probability. And now you might wonder that why I keep taking 3 by 4. This argument will show that 3 by 4 is just some constant. I could have chosen any other thing. So for example, if I had an algorithm which was giving me the correct answer with probability 2 by 3, is it useless? Or can I do something to increase the probability to 3 by 4? This is the question which is asked now. And this is where we will use the tools we have learned before. Let me tell you the problem again. We have a randomized algorithm, two-sided error. Success probability is, let's say, 3 by 4, but we want a randomized algorithm whose success probability is much higher, let's say 1 by 1. So notice that this constant should be greater than half, because otherwise I can just toss a coin and I will be correct with probability half. So that does not give me any advantage. So my probability should be half. Let's say it is half plus epsilon, where epsilon is. And now I want to succeed with much higher probability. So what can I do? Pause the video, think about it. Can you think of a strategy to reduce the error? I think this strategy actually is pretty natural. Remember that in the case of one-sided error, we repeated it and it worked out. In the case of two-sided error, again, we can repeat the algorithm multiple times. So I will get a string 1 0 0 1 1 0, something like that. Let's say I'm repeating it k times, then I will get a string of these answers. Should I answer 1 or should I answer 0? And it's not very hard that I should take the majority of the outcomes. So if I have more number of ones, then I output 1. If I have more number of zeros, then I answer. But can I firmly prove that it is a good strategy? Again, can you think why this is true? The answer in one word or two words is Chernoff. You remember we calculated the probability yesterday that if we toss a coin with, let's say, whose success probability is 0.6. So we have a coin which gives me heads with probability 0.6. And if I toss it 1,000 times, then we saw that the number of heads greater than 500, this happens with very high probability. And this is exactly the argument here. So if the probability of getting 1 here, or the correct answer here, is half plus epsilon, then getting more than half once when I experiment is repeated k times, this probability, so now my algorithm I'm calling it AKX. So AX repeated k times. This is correct is actually more than 1 minus e to the minus 2 epsilon square k. So this comes from Chernoff bound. Notice that my probability is going down as e to the minus k. This is going very fast. So with very few repetitions, I get the correct answer. Epsilon is a constant. So this is given as an assignment to you. So you can calculate this. It is just phrased in different words. It's the same exercise which you did in the previous lecture. It is just framed in different words. I have an algorithm which gives me the correct answer with probability half plus epsilon. If I repeat it k times, then I will get the correct answer more than k by 2 times. That probability is this. Thank you.